Hello everybody, Ud the Science Studio, and I'm back to you with another video. This time it's on reaction writing and how to predict any reaction that comes to you. And to uphold the spirit of chemistry, I'm writing my sick lab coat. So let's begin. So when predicting reaction, there's some basic steps you gotta do. So the first step is to memorize basic reactions. So that way you get some intuition, and then if it comes on paper, you can just immediately write it down. And the second step is to figure out what type of reaction is present. Is it an acid-base reaction? Is it a precipitation reaction? Or is it an organic or nuclear reaction? And the third step is to use intuition. And this mostly comes in the form of oxidation states, which I hope to teach you in this video. Now, this video is not like a 100% study guide teaching you every chemical that's tested on the exam, because chemistry is such a diverse and weird subject with a lot of exceptions. It's not possible. But in this video, I hope to teach you the intuition for you to predict reactions. Because this video is about predicting reactions, not memorizing reactions. So by giving you the intuition, I hope you can get at least 5 out of 6 on the US National Chemistry Olympiad Part 2 exam on the reaction writing FRQ. So let's begin. Something easy straight off the bat is acid-base reactions. So you probably learned this in school or your regular curriculum. So you're going to have an acid and a base reacting to form a salt and water. Let's take a look. Calcium hydroxide plus acetic acid. This is an acid-base reaction. So it'll form water and calcium acetate. So it's pretty straightforward. And if the salt is insoluble by chance, you can just put an S next to it to define its state. Next, we're going to talk about acid and basic solution formation. This usually happens when you dissolve some oxides in water. So to the left side of the periodic table, you're going to have your alkali metals and alkali earth metals, and they will form basic solutions. Now you know their name, why they're called alkali metals. So if you have lithium, right, and water, they're going to react to form lithium hydroxide and hydrogen gas. So it's a redox reaction. Now let's take a look at metal hydrides, especially the sodium hydride. So what predict the reaction? What will happen when you mix sodium hydride plus water? Take a pause at the video and think about what's going to happen. So then salts of sodium are soluble in water, and this will release hydride ions. And hydride ions are really strong bases. They will rip apart hydrogens from water to create an extremely weak conjugate acid, hydrogen gas. So essentially, this will form sodium hydroxide plus hydrogen gas. Let's take a look at non-metal oxides. So what will sulfur dioxide and water form? Hint, it's in equilibrium with something. It will form sulfurous acid. This exists in equilibrium with each other, right? When you form sulfurous acid, right, form sulfurous acid by an acid-base reaction, it will decompose into water and sulfur dioxide gas. And if you also add dissolved sulfur dioxide gas into water, it will form sulfurous acid. Pretty cool. Next thing is P4O10 plus H2O. What will it form? It will form an acid with phosphorus in it. There's two options, phosphoric acid or phosphorus acid. But there's a lot of oxygens here, so we can safely assume that the products will also have a lot of oxygen. And phosphoric acid fits the criteria. H3PO4, a lot of oxygens. Now in dinitrogen pentoxide plus water, what will it form? What's an acid with nitrogen? It will form, mostly these type of reactions form a more common acid like HNO3. will form nitric acid. The fourth, NO2 plus H2O, is a little tricky, so I'll just give it to you. It will form HNO3 plus NO, but just memorize that. And then CO2 plus H2O, it's like the same thing as reaction 1, right? Over here. And it's in equilibrium with each other. So it will form carbonic acid. This is an equilibrium. When you dissolve carbon dioxide in water, right? It forms carbonic acid. This is the reason why usually tap water is kind of acidic. Because all the carbon dioxide in the atmosphere dissolve into tap water and form an acid solution with carbonic acid. And if you also form carbonic acid, it'll decompose, not disproportionate, we're going to get to that. It'll decompose into carbon dioxide gas and water. Whew. Lewis acid and base. A Lewis acid is an electron acceptor due to its partial positive or positive charge. So this involves cations like aluminum 3+, iron 3+, protons, boron trifluoride or aluminum trifluoride. And then Lewis bases are electron donators like NH3, OH, ligands, electron-rich system, benzene anions, because they have a lone pair or negative charge. So we can take a look here. Boron trifluoride plus a negative fluoride ion will form boron tetrafluoride. The lone pair will bond with the positive H plus ion and form ammonium. NH3 plus BF3, the lone pair of nitrogen will get attracted to the partial positive charge of boron trifluoride and they will bond. So sometimes these reactions occur and they're very, very obscure. They have obscure chemicals. So if you see something obscure and doesn't fit into other criteria of reactions, try thinking if it's a Lewis acid or a base reaction. That could help. Precipitation reactions. The only rule I have is just to memorize them, really. But I'll simplify some steps for your memorization by explaining some of the solubility rules. So all nitrates, acetates, and perchlorates, regardless what the cation is, those salts will be soluble in water. And in addition, alkali metals and ammonium, regardless of the anion is, will be soluble. Now let's take a look at OH and sulfide. They pretty much have the same solubility rules, except, yeah, they pretty much have the same solubility rules, and they're usually insoluble, except when they're bonded with alkali metals, group 1, ammonium, or alkali earth metals, group 2. Except Mg hydroxide, magnesium hydroxide, is pretty insoluble, and thus it's a weak base. So yeah, carbonates and phosphates are usually insoluble except when bonded to, I guess, ammonium or alkali metals. Sulfates are usually soluble except those of barium, lead, calcium, and strontium. And chlorine, bromine, iodine are usually soluble except for Ag, Pb, and mercury 1. And then fluorine is usually soluble except in like group 2A, magnesium, calcium, strontium, barium, and lead. So we go. Complexation reactions are usually a type of Lewis acid-based reactions, like the Lewis acid is the metal and the ligand is negatively charged and is a Lewis base, and they react, and that's the Lewis acid-based reaction. So you just want to memorize these. I really can't teach you how to memorize some things, so just memorize these. The important ones are these two, Ag2NH3 plus copper NH34, and then also zinc hydroxide, zinc 2 plus 4OH will form zinc OH 4 2 minus. This is an important qualitative test because if you had a lot of base, it may dissolve, and you can tell if it's zinc or not. Other important complexation reactions is this. Yeah, this is another important one. It's a qualitative test. If you put a lot of if you put a lot of hydroxide and aluminum, it'll dissolve again and form the complex. So you know it's a qualitative test to test for aluminum. I think I said ammonia, I'm not sure, but I meant aluminum. Then nickel plus 4CO will form nickel, yeah. And then you can just remember this. Decomposition reactions. These reactions typically occur like 1 out of 6. So the rule, the general rule is that you release smaller stable gases. So if you take a look at KClO3, right, you'll receive KCl in a small gas of O2. Now if you were to heat up calcium carbonate and decompose it, what will happen? What are the products? It's going to hint one of the, what's the gas? It is carbon dioxide. Usually when you roast carbonate and when you decompose it, it'll form carbon dioxide gas. And if you think of calcium oxide, that's fine. That's fine, I guess. But now you know what the reaction is. NH4 and 2O2. What will it form? This will form water and nitrogen gas. Now what will this one form? What will this one form? There's an extra oxygen, so what will happen? Think. It will form water and dinitrogen oxide. This one's easy. What will this one form? When azide decomposes, what will it form? It will form sodium and nitrogen gas. This one is pretty interesting because this is using airbags, right? And when there's a crash, a spark ignites, and then this will decompose, forming nitrogen gas, thus expanding the airbags so you're safe. And then what's this one? This is a little tricky. Both of these ones are a little tricky, so just go over them. This one releases oxygen gas, and this one has this as a metal. And this one's pretty tricky, just memorize this one. Calcium carbonate plus CO2 plus H2O. So yeah. Now we're moving on to oxidation states. Now these are very, very important. You must master these. So the first step is you need to find reducing agent and oxidizing agent. So what is a reducing agent? So a reducing agent is like a molecule that has an atom at a low oxidation state, right? And these include H2, metals, C2, and H3, H2O2. Low oxidation state means that the oxidation state could be higher. So the H has an oxidation in hydrogen, and H2 has an oxidation state of 0. Metals are usually oxidation state of 0. But then if they become an ion, they'll become a cation. C oxidation state is 0, but you know carbon can have an oxidation state of +2 or +4. Same thing here. NH3 has an oxidation state of -3, and then it will reduce the other molecule by releasing electrons, and then the oxidation state of the reducing agent will get higher. So NH3, right? It'll have an oxidation state of -3, but then nitrogen can have multiple oxidation states like 0, -1/3, 2, 4, 5, can have multiple. And H2O2, the -1, can become 0. However, an oxidizing agent is an atom with a high oxidation state. This is also, so hydrogen peroxide is a bit of a both. I think it's more for an oxidizing agent because the -1 oxidation state is kind of unstable and it will become -2. MnO4 is +7, O2 is 2, Cl2, Br2, I2 are all 0. So they are high oxidation states because halides usually have a regular oxidation number of -1. HNO3 is +5 and OBr is +1. So why do reducing agents have low oxidation state and why do oxidizing agents have high oxidation states? The reason is because that if you have an oxidizing agent right, with a high oxidation state, it cannot get oxidized any further, right? If you were to oxidize it, you have to take out electrons from a lower energy sublevel, and that will cost a lot of energy and is energetically unfavorable. So these atoms will most likely get reduced. Like MnO4 has a manganese has a oxidation to +7, will become something lower. And it becomes something lower by releasing electrons. And these electrons will go to atoms with a low oxidation state. Oh, I got that one wrong. Never mind. I take that back. MnO4 has a +7, right? And it will gain electrons by the reducing agents. So that their low oxidation state becomes higher when they release electrons towards elements that have, or compounds that have, high oxidation states, and thus will be lower. Yeah. So let's take a look at NH3 plus O2. O2 is an oxidizing agent. NH3 is a reducing agent. What will happen? What do you predict about the final oxidation states of nitrogen and oxygen? There's two types of reactions that can occur. So oxygen gets reduced into +2 and nitrogen gets oxidized to +2. So oxygen is -2 and nitrogen is +2. Or that another reaction that can occur is N2 is 0 and nitrogen gets oxidized into an oxidation state of 0, and oxygen is also reduced into +2. I'm just tired of talking, my god. Let's take a look here. So you have dichromate, which the chromium has an oxidation state of +6, and sulfite has an oxidation state of +4. Predict the reaction. What will happen? We know that sulfur can have oxidation states of +6 also, in form of sulfate. So then, as sulfur gets oxidized into a higher oxidation state, the chromium gets reduced. So then, when chromium gets reduced, it will form the Cr plus T, Cr3 plus cation. So we can see that the chromium gets reduced and the sulfur gets oxidized in this reaction. Now we have F2, I think this is, I forgot its name, but Fe2O3 plus CO. Now we know CO is a reducing agent and it will get oxidized. So what will CO get oxidized to? Carbon dioxide. So it will form carbon dioxide gas, and this Fe is an oxidation state of +3 and can get reduced. You could form Fe2 plus or Fe, but I think it usually gets reduced to Fe, just metal. So yeah. And this one, you should just try doing this one. Okay. So Cl2 is an oxidizing agent, right? Not sulfur. What is it? It's not on the list. What is it? Sulfide, I mean. It's -2. And that's the lowest oxidation, one of the lowest oxidation states is sulfur. So, an atom, the low oxidation state is, the compound is a reducing agent. So itself will get oxidized, while the Cl2 will get reduced, and it will form sulfur solid and HCl. Now we're going to disproportionation and comproportionation. So in disproportionation, the reactant molecule is both oxidized and reduced. So it happens in the middle and non-standard oxidation state. Let's take a look at Br2. So Br2 has an oxidation state of 0. But that's not the highest you can go. The highest you can go is like +5, I think, in bromate or something like that. So then it will react to hydroxide to form bromide, which is -1, or hypobromite, which is +1. So this 0, the Br2 is both oxidized to give OBr and reduced to give Br. And also, one good thing is that you normally use H2 as like a side product. There's a side product, there's like a lot of oxygens and hydrogens. So it's like a side product thing to account for the extra atoms. Now guess what's 2CuCl? Guess what's the oxidation state of copper there? What is it? It's +1. So what will happen? It's a middle oxidation state. That's non-standard. That's not a typical oxidation state for copper. It will form copper metal and Cu2 plus 2Cl, because this +1 gets reduced to 0 and oxidized to +2. And this one's a decomposition reaction. What will happen? You gotta just know this one. This will form O2 gas plus H2O, because this -1 gets oxidized to 0 and reduced to -2 oxidation state in oxygen in water. Comportionation reaction is the opposite of disproportionation. So this one you must know, it's just the reverse of this reaction. Oh no. Let me just get my charger really quickly. So this is essentially just the opposite of disproportionation. So then you have 0 oxidation state and +2. This will form a +1 copper product. Yeah. Time to nuclear chemistry. This one appears, I think, once on every set of problems they give you. So in alpha decay, this usually happens for like heavy compounds like bismuth, polonium, lead. So then usually you release a helium nucleus. And then beta decay is you lose an electron. So in this one, essentially you lose an electron, and then the neutron will lose its negativeness and will form something positive. Because if you think about it, this is not true, but like a neutron has something positive and has something negative, right? If you take the negative away by releasing an electron, it'll become positive, or a proton in this case. And this usually happens for large neutron to proton ratio isotopes. Gamma decay, it's not really a reaction. It's not really a reaction. It's just like you are releasing energy. Positron emission is where you release a positron or a positive electron. So a proton will lose its positiveness and will form something neutral, like a neutron. And electron capture is where a proton will also lose its positiveness, because something positive plus something negative will form something neutral and will form a neutron. Now basic organic reactions, these also occur. So sorry, I just was talking a lot. I was just practicing before I made this video, and then I just talked a lot. Just sorry about that. My cheeks are hurting. Let's go. Addition reaction examples: so halogenation, the bromine attaches to the double bond, same with water. Hydrogen, and then polymerization is where the double bond forms a bond with the double bond splits and links with other vinyl chlorides. And then one interesting thing about addition reactions is that, let's say you have this molecule over here, my cursor is pointing over here. And if you react with hydrobromic acid or water in acidic solution, where will the bromine atom go? Will it go here or here? The answer is that the bromine atom will go, or the hydroxide, the OH group, will go in the middle, whereas the proton will go in the end. This is because in the reaction mechanism, which I highly encourage you to read, we'll have a stable carbon cation in the secondary position. So, yeah. Substitution reaction is just a group of atoms replace with another ones. So just find out the nucleophile electrophile, like over here. This one replaces the chlorine group. So we're talking about electrophilic aromatic substitution and esterification. So in esterification, we have a carboxylic acid plus an alcohol, and this will, in concentrated acidic solutions, you will form an ester. But then if you dilute the acidic solution, you will shift the equilibrium to the left and will form a hydrolysis reaction. And electrophilic aromatic substitution of benzene, you have chlorine with FeCl3 will form chlorobenzene with HCl. Nitric acid will form H2SO4. That in water. Don't forget these guys. Sulfur trioxide plus that will give you this. Methyl chloride will give you this, and acetyl chloride will give you this. So these two. This one is Friedel-Crafts. Friedel-Crafts. I forgot. This is acylation, and this is Friedel-Crafts alkylation. So I will encourage you to read mechanisms on these guys. So essentially, with the Lewis acid catalyst, you will knock out this, and this group, the CH3 group, will replace an hydrogen atom and form a CH3 bond. And this one, the same thing occurs for this one, forming HCl byproducts. So yeah. Radical reactions, usually if you have bromine in heat or light, will replace a hydrogen atom with bromine, and the bromine likes the more substitute region because it has a more stable intermediate, and this was a major product. And chlorine really doesn't care if you're over here or there, it doesn't care. So let's put some reactions into practice. So this is from 2009. So let's begin. So solid calcium is heated in nitrogen gas, so calcium plus nitrogen gas. So I think this is a redox reaction. I haven't quite. So I think calcium is 0 to 0. Calcium will of course get oxidized because it cannot have a negative oxidation, so it's only a positive. Nitrogen can have a negative. I think it will form nitride. Oops, not that. It's azide. I think it will form, because I think that's usually more, I think that's like the likely option when nitrogen is in ionic compounds. So I think the reaction will be, oops. I think that's the reaction. Good. Easy one. Solid sodium ethoxide. Oh, ethoxide, that's like a base, right? Yeah. Deprotonated ethanol. Now it's added to water. Keep in mind, this is blind and I have not done this before. So that's a base. Okay, yeah, so it'll form ethanol, an acid-base reaction, and hydroxide. Solution of magnesium sulfate plus barium hydroxide. So like a precipitation reaction, I think. Yeah. Double displacement, barium sulfate solid, and magnesium hydroxide solid. Pretty easy right now. An acidic solution of potassium permanganate. So MnO4. I'm just ignoring like potassium and sodium because like they are what? Spectator ions. That to the solution of sodium sulfide. So sulfide is SO3, yeah, 2 minus. And an acid solution. So this is +4 and this is +7. This is an oxidizing agent, will get reduced. And usually Mn2+ forms in acidic solutions if it gets reduced. MnO4 is neutral and Mn- is basic. And this is an acidic solution, so we're going to form Mn2+. And when you oxidize sulfite, you will get sulfate. Because this is +6 and that's +4. Okay. T. Radium. What's done in the periodic table? That is radium, right? Where's radium? Radium is 88, right? It goes alpha decay, will release helium, and that will become 86 and 218, and that will become, what is it? I think it'll become radon, right? Radon? Francium lose 1, yeah. And then lastly, 2-propanol. You also didn't know naming conventions, saw some of these. It's heated in concentrated sulfuric acid. I think that'll just be a dehydration reaction. I can't teach you all the organic reactions in this video, but I can teach you like some. So let's check our answers. I did not look at them, I just brought them up. Trust me, guys. So then calcium plus nitrogen, yep, we got it correct. Yep, we got it correct also. Yep, also got this one correct. Yep, also this one correct. Yep, this one correct. And yep, this one correct too, so we got everything correct. That's good. Let's do another one, 2010. Just do 2010, so let me delete this one. Delete. Okay, let's go to library. 2010 reaction writing. So let's begin. So this is on 2010. Solution of hydrochloric acid, so we have HCl. We should also write states of matter. I'm too lazy to do it. And silver acetate. So this is just a double displacement reaction. Acid, base, and precipitation, I guess. So we're going to have AgCl plus acetic acid. Easy one. Let me just erase this so I can have more space. A small piece of potassium is added to water. I just taught you guys this, so it's potassium hydroxide plus H2 gas. Simple. Concentrated hydrochloric acid. Oh, so this is a complexation reaction, right? So cobalt 2 plus 4Cl will give you aqueous. I think it's easy. So this is a complexation. D, acidified solution of potassium dichromate, right? So dichromate is Cr2 plus 7 plus 10. So this one is plus 6 and this one is plus 2. So this one is a higher oxidation state, so this one will get, I think, reduced. Yeah, reduced into C3, and then we're going to have this one get oxidized. Then tin can have oxidation states of plus 2, 0, plus 2, and plus 4, and this will get oxidized into plus 4. We'll have SN plus 4. And this is in what? Acidified. This is acidified solution. And you account for the oxygens and water, this will just form H2. Methyl ethanoate. So you also have to know how to name stuff. So you have hydroxide plus OH. Saponification, right? So like reverse esterifications, you're gonna have I just know these. So one, yep. And then you're gonna have, hold on, let me just make this more smaller. Carbon 14 undergoes beta decay. So you have carbon 14. So beta decay is you're gonna have release a beta. So kind of this. So you have a neutron, right? It's both positive and negative. But then since you take out the negativeness by taking out an electron, this neutron will become a proton. So we're going to have plus 7, 14. I think we're done. Let's check our answers. So yeah, we got this one correct. We got this one correct too. Oh, I think I forgot to give in the reaction of acid. I think I forgot to give the reaction of H plus SO4 to give. I forgot to do that. So I forgot to do a side reaction. So I think I like lost 1/2. So yeah. Yeah, I got this one correct too. And I got this one correct too also. And I got this one correct too. So using these methods, I think I got only 1/2 wrong out of 2 FRQ. So I think it's very good.